Hi. In the previous episodes, we saw the problems where it was already given that the object which was rolling was already in pure rolling. Now, in next few episodes, we are going to encounter the cases where the object which will be rolling will not be already rolling. For example, let's say there is this rough horizontal surface. Now we can take both cases. Rough horizontal surface and the smooth surface. So first of all, what I'm taking is the rough horizontal surface here, and there is a disc, let's say a sphere, ring, it can be anything. So let's say there is a disc which has been given an angular velocity omega, and the disc is kept on the rough horizontal surface. So let's say the coefficient of friction here is mu, and this is the disc that is kept here. Again, I'm leaving some gap here. You know why I do that? Because I have to draw arrows and make diagrams and write some values and all that. So I'm just leaving a gap. You can understand that whatever this object is rolling, that is of course in touch with the ground. That is, it is in contact with the ground. All right. So what is given here? It is given an angular velocity omega. It is not given any translational velocity. All right, and it is just kept on the surface. Fine. Now, what will happen? So whenever you have this kind of cases, so how do we do that? So first of all, understand one thing. As you keep this, because see, in the problem it is not given that it is pure rolling. All right. So what is the first thing? See, whenever it is already given that it is pure rolling, you know that there is no slipping and the friction is static and all that. But when it is given that it is there is an angular velocity omega, and nothing has said that whether it is pure rolling or not, then you will check whether it is slipping or not. So to check whether it's slipping or not, what do? What we do is that we check the velocity of this point and velocity of this point. So what is velocity of this point of the ground? That is 0. What is velocity of this point? Because this is omega, and let's say if its radius is r, then velocity of this point is omega r. Right? So velocity of this point is omega r. And now because these 2 points are different velocities, so this rolling object will actually slip. So this will be slipping with rolling. And now because it will slip, what will happen is that there will be a force of friction that will act. Now tell me, in which direction it is slipping? It is slipping in backward direction. And since we also know that it is slipping, we can directly imply that the friction that will be acting here is going to be kinetic friction. Alright? And we know that kinetic friction always acts in a direction which is opposite to that of slipping. So it is slipping in backward direction. So there is going to be a force of friction that is going to act in forward direction, and that is a kinetic friction. Why kinetic friction? Because it is slipping. Why it is slipping? So you can easily understand that. So the value of kinetic friction is going to be mu into n. Now you understand, this is the case. So we got about friction. Now what will happen? To see what's going to happen next, what we are going to do is that we are going to break the motion into two parts. So here, this is what I'm doing. So first of all, let's consider only translation part. So this will just translate. Forget about rotation. We know that there is a force of friction that is acting. Do we need to consider omega, omega r and all these things? No, because omega, omega r, these are all the effects of rotation. All right. What is our initial translational velocity? What was initial translational velocity that was given to this object? It was 0. There was no initial translational velocity given to this object, right? So now a force mu n is acting. Let's say its mass is m and its moment of inertia is I. Now what's going to happen? Because on this mass m, there is a force mu n acting. This mass is going to accelerate. I'm again telling you, forget about rotation. A force is acting on a mass m. Just consider translation. I'm considering translation part. After this, what I'm gonna do is that I'm gonna consider the rotation part separately. Alright, that's our strategy. So there is going to be an acceleration of mu n divided by m. This is the acceleration with which this will start moving ahead. And as it will start moving ahead, because of this acceleration, its velocity, translational velocity, will keep on increasing. So right now when you're dealing with translation, I'm again reminding this again and again since last all the episodes, that always deal separately. When you're dealing with translation, forget that this is rotating. Don't even let it come to your mind. So it is just translating. Alright. So this is an acceleration mu n by m. And we know that its velocity is going to increase with time. So velocity, initial velocity is 0, is at, and a is mu n by m into t. This is not a formula or anything that you need to remember. Just understand the dynamics, how it started. We gave it an omega and kept it on the surface. Due to the omega, there was an omega r. That's what there was a difference in velocities at these 2 points. So it slipped. As it slipped, what happened? As the motion started, see, from the beginning itself it was slipping. So in the beginning itself the friction acted. As the friction acted, now we are seeing it in 2 parts. So first of all, in translation part, we saw that due to the force, there will be an acceleration, and due to that acceleration, the velocity will keep on increasing in this direction, right? So this v whatever it is increasing as the time is passing. So I'm just marking an increasing arrow for this. Now let's come to the rotation part. So how we are going to deal with the rotation? So let's say this is the object and it was given an initial angular velocity. Because it is an initial angular velocity, let me call it omega naught. Alright. So this is initial angular velocity of omega naught that I've got. Now let's say its radius is r, and we understand that there is again a force acting here. The value of this force is mu n. Now tell me, to consider rotation, now forget that it is translating. Just think that it is fixed about its center of mass and it is just rotating and there is a force acting. Now because we are focusing on rotation due to this force, we will focus on the torque of this force. Since the radius is r, we know that the torque here is going to be anti-clockwise, right? This torque is anti-clockwise. See, initial angular velocity was clockwise, so its initial tendency of rotation was clockwise, but the torque due to friction is, this torque is here actually mu n into r, and due to this torque there is going to be an angular acceleration alpha, which is tau by I. We know that tau is equal to I alpha, right? So alpha is going to be equal to mu nr divided by I, whatever is moment of inertia. Moment of inertia will depend on what kind of object this is. You know that different shapes have different moment of inertia. Alright. So now once we have got this value of alpha, we understand that this alpha is opposing in this its initial velocity. So what will happen? The angular velocity will keep on decreasing. Alright. So any angular velocity as the time passes will be omega naught minus alpha t. Alright. So this is how, and this value of alpha is what you can plug in here. So you understand one thing. Now see, a very beautiful thing is going to happen which you can visualize here mathematically without doing any physical experiment, and that's the beauty of theoretical physics. So what you see here is that you give it an omega naught. As you kept it on the ground, it slipped because it has some, here it was of course omega naught into 1 initially. So because of this slipping, there was slipping because there was a difference in these velocities, and you initially only gave it rotation. Due to this difference in velocity, there was slipping. Due to slipping, there was a presence of kinetic friction. How did we conclude the direction of kinetic friction? We knew that it is slipping in backward direction. So the friction was acting in forward. See, kinetic friction has a fixed value and a fixed direction. Fixed value is mu n, and direction is, if you have to guess or judge the direction of kinetic friction, always guess the or always find out in what direction the object is slipping. So we understood that object was slipping backwards, so friction acted forward. Now you broke the motion into two parts and dealt separately. Translation, while translation you forgot that it was rotating, and while dealing rotation you forgot it was translating. I'm again summarizing. So I'm just concluding here what happened. Due to this, because initial translational velocity was 0, no initial translational velocity was given, and there was a friction. Due to this force there was an acceleration, and due to this acceleration this v started increasing as the time was passing. And here, due to this rotation, when we are considering rotation, there was a torque, which torque was in anti-clockwise, initial velocity was clockwise. So as the time was passing, the torque produced an angular acceleration, and this angular acceleration will keep on decreasing angular velocity. Now think about this point. Let me show you here. Now once you have understood this whole story, now focus here. So this was the ground, and you know that what is the net velocity at this point? At any time, due to translation it is v, and if it is at any time this angular velocity is omega, then due to the rotational motion, the velocity of this point is omega r. So we know that what is net velocity of this point at any time? That is v minus omega r. And you understand one thing, that as time is passing, v is increasing and this omega is decreasing. Initial velocity was omega naught. So what will happen? This will keep on increasing. This value was initially 0 and this value was initially omega naught r. So what will happen? V will keep on increasing and omega will keep on decreasing. So V increases, omega decreases. A time will come when V becomes equal to omega r. See, initially omega r value is going to be higher because V is increasing from 0. So V will slightly increase its value, slowly increase its value, and omega will slowly decrease its value. So a time will come when V will become equal to omega r. See, V will not become equal to omega, but V has to become equal to omega r. And at this time, what is going to happen? At this time, the net velocity of this point is going to become 0, and a very beautiful thing, once this point's velocity becomes 0, tell me what is the velocity of this point? That is also 0. Once this point's velocity also becomes 0, these two points have same velocities, and what's happening? Pure rolling starts. So what you saw, that you gave an angular velocity initially and you kept it on the surface. Due to that these two phenomena happened, and you saw that after some time pure rolling started. And once pure rolling started, you know what is the friction? The value of friction here is static. You know that after some time when this becomes equal, the velocity of this point becomes 0, which is equal to this point, there is rolling without slipping, and at that time friction is static, right? And that static friction can be anything. That static friction, I told you, can be anything from 0 to mu n. And in this particular case, because there is no other force acting, the value of that static friction will remain 0. Alright? So that this force which is there will vanish after that. So once pure rolling starts, friction just vanishes. It becomes a static, and the value of that static friction is 0. So at that time, no frictional force is acting, and that once there is no force acting, this velocity, this v, will stop increasing, and this omega will stop decreasing, and it will remain at the same value, the value at which v is equal to omega r, and it will keep rolling forever. That's the story. We'll see one more example like this in the next episode. Thank you. Have a nice day.